Good afternoon, everyone. Hope you had a lot of coffee. All right. So let's see where we were. Okay. So I've defined a quantum code with a set of stabilizer generators. These are like the rows of the parity check matrix. So every stabilizer generator imposes a constraint on the Hilbert space, and the set of state that obey all these constraints forms the code. The code is a subspace of the Hilbert space of dimension 2 to the k if there are n minus k stabilizers. All right. So if you start with a code state and it picks up an error, and we've assumed so far that it was a Pauli error, we can get back to this in a couple of minutes. Then you have a state with an error on it, and if you read if you check the eigenstate, the eigenvalue of a given stabilizer generator, you're going to get either plus or minus 1, and this will give you a fingerprint of the error that we call the error syndrome. And as always, your goal would be to figure out what was the error that led to this syndrome. And for this, you must assume some underlying model of errors. Okay? Then the next thing I said is that this is not quite optimal. Although this would be optimal in the classical case, it's not quite optimal in the quantum case because you can have degenerate errors. Degenerate errors are errors that, as far as the code is concerned, have exactly the same effect. Okay? This is because they are related by an element of the stabilizer, and by definition of the code, the stabilizer acts like the identity on anything that's inside the code. Okay? So clearly, such errors cannot be distinguished because they lead to the same physical state, nor do they need to be distinguished. So the last thing I said is that you should not be optimizing this thing. You should be optimizing something like this. Sum over all E prime that is similar to E, and similar here means it's E multiplied by any stabilizer. Okay? P of E prime given S. You should just group all the errors that are equivalent, i.e. related by a stabilizer, and add up their probability and then pick up the thing that maximizes this. Okay? This is kind of, you don't need to do this. This is optional, but it is the optimal thing to do. Okay?
But why the choice is E? I would have thought it would be S, but E is the error.
Yes.
So we don't choose the error. We choose the stabilizer.
Sorry. Oh, so this small s is the syndrome. So it's the set of plus and minus 1. So once you know the syndrome, some errors are ruled out. The ones remaining have their a priori probability just renormalized because you've removed some possibilities.
Yes, no, but maybe it's not choosing, then it's finding E.
Yes, so you want to choose E that maximizes the probability of E given the syndrome that you've seen. But now I'm saying you're going to choose the equivalence class. Let me just abuse notation. Yes, let's pick the equivalence class of errors that optimizes this probability. Okay? And then you correct with any of those errors. Anyone has the same effect. Is that good, the distinction? All right, so this was about error degeneracy. Yes.
For those of us that are paranoid, I mean, there's nothing wrong, but for those of us that are paranoid, I guess you have to think about your logical qubit might be entangled with something.
Of course.
And if the two degenerate errors, like which one actually happened, depended on the state of the thing you're entangled with, then is it true that it would not be a global minus sign that would sometimes happen?
Oh, no. No, it's a good question. No, it's yeah, it's a global sign. I mean, it's a global minus sign, right? So if you had, you know, 0, because the minus sign goes in front of the entire code space. Right? So if you had 0, 0, and this one was in the plus 1, 1, and you had like, you know, SE, and then you apply E, but you apply it, sorry, this is, you apply this to the second qubit.
Yeah, I'm just saying if the,
What?
you had two different members of the equivalence class that differed by,
Yep.
with a minus sign, and you got one to the 0 and
No. That's yeah, that's right. So so right, this here is plus or minus the identity on the entire code space. If it acted differently on different code states, that would be a problem. But here, I mean, this is kind of an operator,
okay.
an operator identity, and it acts on the entire space uniformly. That's very important.
Okay, good.
All right. So just a word about this assumption here. It sounds a little bit crazy if we can only correct Pauli errors, because it's kind of the beauty of quantum mechanics is that you can do more things than Pauli operators, right? You can rotate by arbitrary angles, and you can do all sorts of things. So why should the environment be restricted to such things? Okay. Well, I don't want to go into the details because I don't have time to prove this, but it turns out that, like all of quantum mechanics, error correction is a linear procedure, linear in Hilbert space. So if it happens that you can error correct a bunch of Pauli errors, you will be able to error correct any linear combination of them. Okay? So for instance, if I have an error, so if psi goes to e to the I theta x psi, well, I can write this as cos theta psi plus I sine theta x psi. Okay? And then when I'm going to measure my syndrome, I'm going to see either no syndrome or the syndrome associated to an X error. So the measurement, the syndrome measurement, sort of collapses onto a Pauli error, and then you just correct. Okay? So if there is a set of Pauli errors that you can error correct, then you can error correct any linear combination of them, and that includes unitaries and all sorts of things like this. Yes?
I mean, the way I always understood this is like basically by measurement you discretize your errors.
That's
Which is basically the only way you can do error correction.
that is yeah, that's essentially the idea.
That's actually the news that Joan explained.
Yeah, well, yeah, there are some fine prints to that.
Okay.
But okay, the claim is true as long as you're considering only things that you can correct. Okay, but in there's never, you never have a noise model that constitutes of only operators that you can correct. For instance, if every qubit gets rotated by some small angle, okay, then, you know, I will have this operator, tensor n. If I expand this in this way, I will have all possible combination of identity and x. I can't correct all of those.
Yeah.
Okay, so so yeah,
That goes beyond the distance of the code.
it goes beyond the distance of the code. That's
The
right.
code is good anyway.
Yeah, if you have a good code distance, you should be good to correct any reasonable thing. Yeah. Yeah. All right. So maybe we just define code distance. We just mentioned. So how would you define this? Well, any question on what we've just seen? No? All right. So code distance. How are we going to define this? Anyone has any idea? So for some reason, I think Dan Gottesman introduced this, use a double bracket when it's a quantum code. So it's going to be much of the same number of qubits, number of logical qubit, minimum distance. And by the way, the number of stabilizer generator is equal to n minus k, as in the classical case. Okay? So how should the minimum distance be defined? What was it classically? It is the smallest bit string that is non-zero, but that is also has no syndrome. Right? That was the definition. The smallest bit string that has no syndrome. Okay. So what would be the analog here? It would be, what's the smallest Pauli error that commutes with all stabilizers? Agree with that? So this will not be detected. Such. And sorry, yeah, I use the word smallest here. I mean, by smallest, I mean the lowest weight Pauli. And the weight of a Pauli operator is the number of elements. So if you have an n-qubit Pauli operator, it's the number of occurrence that are not the identity. Okay, if you have x, y, or z, you add 1. If it's an identity, it doesn't count. So smallest Pauli that is not the identity, for such that E commutes with all stabilizer. So this is an error that is undetected. So it should be taking a code word to a code word. But there's a bug with this proof. It's not complete. Sorry? It's a definition. It's a bad definition. Because you want the minimum distance to be like the smallest thing that can be bad. Okay?
So that it should be equal to
Sorry,
0.
yes. Equal to 0. Yeah, that's not the bug I was talking about, but yes. Thank you. Huh? So you don't want... Okay? Because the stabilizer effectively is the identity. It acts as the identity on the code space. Okay? So if you have an error that's a stabilizer, well, that's a harmless error. Doesn't do anything. Okay? So you don't want to be counting those. Okay. So that's sort of, I guess, all I wanted to say about the formalism of error correction. Oh, maybe one last thing. Well, oh yeah, well, let's talk about CSS code. Carl Lebanc, Shore, and Steen, these are just the name of 3 people. And these are just a special class of codes. They have the property that stabilizers are either all x, well, no, sorry. Each stabilizer is either all x and I or all z and I. Meaning there's no stabilizer generator that has x and z's in them, or y's for that matter. Okay? All stabilizer, generator is either all xi or all zi. Okay? And this is a pretty useful feature because what you can do if you have a CSS code, you can view it as two classical code. One that corrects for bit flip and one that corrects for phase flip. Okay? So pretty much all you know about classical coding will apply to a CSS code. So you'll first decode for X errors and you'll decode for Z errors. And if you have Y error, they just create one of each because Y is equal to X times Z up to a phase that we don't care about. Okay? So, so this is pretty neat. And also, it allows for really to import a lot of things from classical coding theory. So one thing we'll do, if we have a CSS code, instead of using, this is just a handy notation. If we have something like XIIXIX, we will replace this by 100101. Okay, I suppose you get the pattern. So if a Z stabilizer is, let's say, 011010, and a an X stabilizer is 111010, do they commute? Okay, so do these bit string represent Pauli operators that commute, yes or no? No? Why? Because they overlap 3 times, right? So for those of you who did not understand, X and Z anti-commute. So if you want to move an X string across a Z string, you need to look at how many times X and Z overlap. If it's an odd number of times, you will get an odd number of -1s. So you'll get a -1, hence they don't commute. If there's an even number of overlaps, so in this case there were 3 overlaps, so they don't commute. Okay? All right. So it means that, so yes, so if there was an even number, then they would commute because you'd have an even number of -1 sign. Good? All right. So remember the Hamming code. I don't. So I have to go back. Anyone remember this parity check matrix of the Hamming code? Yeah, that's right. Yeah, okay. Hamming code. I may write it in a way that kind of permutes qubits around. Okay, this is the Hamming code. If you use this parity check matrix and say, all right, I'm going to use this parity check matrix to create my X stabilizer and my Z stabilizer. So this is going to be a self-dual CSS code. Not only is it a CSS code, but the X part looks exactly like the Z part. Okay? So we call this a self-dual CSS code. I claim that you can build a self-dual CSS code out of this one. Okay? Why is that the case? Because H transpose is equal to 0. You can easily check, right? Take these, well, first of all, every row is orthogonal to itself because they all have an even number of 1s. And any pair of rows are orthogonal. Take these two. 1, 2 overlap. Take these two. 1, 2 overlap. And let's do it all. These two, 1, 2 overlap. Yep, they're all orthogonal to each other. So if I define, so my code would be, this matrix with Z, this matrix with X, and these would commute. I've just shown this to you. And this can correct any weight 1 error. Why? Because the Hamming code could. Right?
Sorry, I was looking down when you said this.
You got to pay attention.
Yeah, sure. What is the analog of this string that tells me where the x is?
Yeah, so I'm going to take each of these row. I'm going to associate an x operator to each of those. So,
There are going to be 3 x stabilizers.
yep, and so on, right? I'm going to have 3 x stabilizer, 3 z stabilizers. Therefore, there's going to be 1 qubit in that code because you have 7 qubit and 6 stabilizers. It will be able to detect and correct any weight 1 Pauli error, right? Because if that error is an X error, the thing will behave just like the classical error correcting code. You will pick up no X syndrome because X commutes with X. So you will pick up a Z syndrome that matches the pattern of a single bit error on the classical code. Is that clear to everyone? Should I go through the exercise? Please, who wants to see more details? Or is that clear to everyone? Great, okay. So the stabilizers are this. And lastly, and then the same thing with Z, okay? Excuse me?
Is this the distance 3, CSS?
This is the distance 3. You could call it Hamming code. It's also called the Steen code. So it's a 7-qubit code, Steen error correcting code. One of the first code that was... So these are the 6 stabilizer generators, okay? Let's suppose I have this error. This error. What stabilizers are going to pick it up? These are not going to pick it up, right? Because these all commute with that error. So I want to know which of these stabilizers don't commute. This one commutes, this one does not commute, this one commutes. So my syndrome everyone agrees with that? So, but this is the same syndrome as a bit. So if I look at, this is the Z part, this is the X part, meaning the first 3 are associated to those, and the last 3 are associated to those. This part will only ever pick up Z errors. This part will only ever pick up X errors. Let's treat Y errors later, okay? This is the syndrome that you would get if you applied a classical error on the second bit. Okay, it's the same. It's gonna the syndrome associated to error are going to be the syndrome associated to the classical error. But if the error is an X, it's going to be associated to the Z part. If the error was a Z, it's going to be associated to the X part. Is that better? Yes. All right.
So now what do we do with Y? We're gonna know.
Oh yeah. So if it's Y, okay, let's say, what would be the syndrome of this? So you get 2 copies of the syndrome, right? Because you have an X signature and a Z signature. So if you have just an X syndrome, you know it was a Z error. If you have only a Z syndrome, you know it was an X error. If you got 2 copies, you know it was Y.
Provided there is only one error.
As long as there's just 1 error, this is a distance 3 error correcting code. It corrects only weight 1 errors. Yeah. Okay. Right. So, okay. So now we can, this is pretty neat because we can borrow a lot of stuff from classical coding theory and import it straight into quantum theory using the CSS formalism. Okay? Yes?
Can I see easily why the distance 3?
No. Well, now you should be convinced that it's at least distance 3. Why? Because it corrects everything of weight 1. Right? So remember, you can correct anything of this of weight d minus 1 over 2. So d must be at least 3. Okay, because, well, this argument shows that you can correct anything of weight 1. Why is it actually distance 3? You have to find something that has weight 3 that will not be detected. Right? Then that is not generated by those and that is not detected. Here's something. This won't be detected. Right? It will commute. Moreover, it is not generated by those guys. How do I know? These only generate even weight things. And this is odd weight. So it can't be generated by those. Hence, it's not a stabilizer itself. And it's not detected. Therefore, it's an undetected, harmful error. Okay? So this shouldn't be obvious. Finding the minimum distance is a hard thing. I happen to know for this code because it's a simple one. But in general, if I give you a list of stabilizers and I say, what's the minimum distance? Super hard problem. It's NP complete. Yes?
If you're like in the classical cases, it's not true that an error of weight 1 flips just one stabilizer. Like in this case, we saw that the Y error.
Yep.
Is it like?
It was not true. It was not true. So like if I classically, if I flip this bit, I'm going to have 2 syndrome, right?
Oh yeah, sure. No, it's
Yeah. Okay. Other questions? Yes?
You just back up to saying that that was an NP complete problem. So
Yes.
do you know the
Finding the
distance
minimum distance of a code.
code that I might use to
Yep.
trump that.
Yeah. Makes life more exciting. Yeah. You can always brute force search. But yeah. Sometimes you can be a bit clever, but there's no... I mean, if the code has structure, sometimes you can exploit it. Like surface code will be able to compute the minimum distance. But generally speaking, it's hard. Okay. Yeah. Okay. Now I want to get something very important across. So it sounds like we have ourselves a machinery to just generate quantum codes out of classical codes. And if the classical codes were good, the quantum code's going to be good, right? Because if the classical code detects a bunch of errors, then the quantum code is going to detect a bunch of errors. Okay. So why not just use the CSS construction to get Ldpc, and we'd be done. Okay. All right, let's try to explain this. So let's try to construct quantum Ldpc code. So for the X part, so I'm going to do what I said, right? I'm going to take a random sparse graph, look at the parity check matrix that it represents, right? And I'm going to say this is my X part. Okay. This is the kind of code we've been talking about so far. What do we know about these codes? That we know that they're very good. Typically, they're very good. Okay. What does this mean? It means that they have no low weight code word, right? They have a large minimum distance. But asking that these guys commute with those sort of means that this one must have a bunch of low weight code words. You see what I mean? Look, here, right? We want an Ldpc code. This means that we want a bunch of low weight stabilizers. Okay? So let's pick a bunch of random low weight classical stabilizer, classical check, and turn them into X stabilizers, say. All right, so we got our low weight stabilizer, and because it came from a quantum classical Ldpc, we know that these are good codes. Okay. So now we want to pick Z stabilizers. We'd like them to be low weight, but they must also commute with those. But there's nothing of low weight that commutes with those because these came from a classical Ldpc code. And a classical Ldpc code has a large minimum distance. There's nothing of low weight that commutes with them.
Can I repeat the argument?
Yeah. All right. So,
I think everybody was waiting for that.
yeah. Yeah, definitely. Okay. So let's say we create X stabilizers by taking the parity check matrix of a classical LDPC code and just replacing zeros with identity and ones by x's. Okay? So we got ourselves the x stabilizer. Okay? Now we would like to construct the z, pick some z stabilizers, anything. But we want them to be low weight. We also want them to commute with those.
Why can't you do what you did here and take the same code, just replace the X with the Z?
Because typically, a code is not self-dual. This is a very special property.
So you need an even number of ones, and that's the problem?
But no, but here's the thing. This would be this is kind of, for an LDP, a classical LDPC to obey this would be a very bad LDPC. Okay? Because look, okay, I see this is maybe a slightly subtle argument. So, okay, so pick H, some parity check. Of some classical LDPC. It has a large distance. Hence, there are no low-weight solution
I'm there. Slow, but I got there.
H.
The students will follow you.
There are no so the lowest weight y that obeys this equation has weight d, and d is large. Okay? Because it's a good code. All right, now turn H into Z, or what was I saying? I was saying your X stabilizer. Okay, so now I'm now looking, or was there, I want to construct an H prime that will define my Z stabilizer. Is that good to everyone? Right, so I have my X part. It came from this LDPC code. I want to define H prime that will define my Z stabilizer. H prime must obey two things. H prime should be sparse, because we want a quantum LDPC code. It should obey H prime transpose equals 0. Because this means that the X and Z stabilizers commute. But this is a contradiction, right? We just said that there was no low-weight solution to HY equals 0. So there can be no sparse matrix that obeys this. Yes?
So, is the following picture correct? So imagine I'm just trying to correct, I make X stabilizers. I'm just trying to correct Z errors.
Yeah.
So don't think about Z stabilizers, think about these things as errors.
Yes.
And it has a huge distance.
Yep.
So I won't get fooled until I have a really large weight Z operator.
Yes.
And once I'm fooled, I should say, oh, I should call that a stabilizer, not an error.
Yeah. And this can't happen. So it can't be sparse. Does everyone understand? Or raise your hand if you still have issues with this argument.
Don't be shy.
I don't believe you. That's slightly better still. Okay. Okay. So with this equation, so the purpose of this equation is that this inner product encodes the commutation, right? If I take a Z string and I multiply it, so I have to, the transpose is only, you know, because I want to take the product. So I have two strings, I want to know if they're orthogonal, I take the transpose of one, I multiply them, I must get 0 mod 2. Okay. So saying that this is 0 means that every row of this matrix is orthogonal to every row of this matrix. And this tells me that the X and Z stabilizers commute with each other. Is that good? That's definitely something we want, right? We want commuting stabilizers. But I also want every row here to be sparse, of low weight. So this means I'm looking for hy equals 0, where y is of low weight. But there is no such solution because h was a good code. Okay? So I sort of need, so here's the trick. You could say these things are all errors that are undetected by this. Right? So this is a bad code, it doesn't detect these errors. But in a quantum code, you say, no, 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 these are stabilizers, so I don't need to be correcting those. I'm making them part of my definition, and therefore I don't need to correct those. So to construct a quantum code from this CSS construction, you need to start with a code, a classical code, that has kind of two types of code words. A lot of low-weight ones, which you're going to declare to be stabilizers, and a bunch of high-weight one, but nothing in the middle. It's really special, right? You need a code that has low-weight code words and high-weight code words. You take all the low-weight one, you declare them to be the dual stabilizers, so you don't need to worry about them. And the high-weight one are going to be the errors you care about. Okay?
It's actually possible to have something like this because, I mean, because of linearity,
Yeah, you have.
the between words should be constant.
I'm going to show you how to achieve this. It is possible. Yes?
Are classical codes ever really, it feels like classical codes are never designed with this.
No, no. It takes a very special design. So this is why, yeah. Yeah, it's like there's no reason whatsoever to ever look for this classic. All right, there's just no purpose. So everyone understands this now? Okay, so yes?
The conclusion is that we cannot use the CSS construction.
You would have to start with a very special classical code. So random constructions will certainly not work. And unfortunately, this has been our main tool for 50 years. We just construct random graph and it just works perfectly well. It's not going to work here. So we have to be very clever about it.
But this is a fundamental problem. If you have X and Z, they will kind of like if your code is too good, then the other side of so what you're saying is that the solution cannot be code words that only have X's and code words that only have Z's. It has to be.
No, I'm not saying that because you would have the same kind of argument even if you generalize and have Y's in there and so on.
Well, or X and Z's on the same code.
Well, okay, you could say, well, I'm just going to have a code with only X, but then you won't detect X errors.
No, but I guess in the CSS you force the code words to only have identities and X's or
Yeah.
identities and Z's. If I allow you to have X's and Z's in the same words, then is that better?
I would say we don't know. The solution I'm going to propose does not use that freedom. No, it's a CSS code, but it does something else. It doesn't just take a classical code and say, I'm going to declare this to generate my X guys, and then look for Z. It's going to do something more clever.
But isn't this fundamental? If you take your code and take all the X words and say this could be a classical Ldpc, and then you keep saying the same argument and saying that you can't be too good.
No, okay, so if you take the X stabilizers of your quantum Ldpc code and you say, I'm going to make a classical Ldpc, It would be a very bad code.
I see.
Yeah. All right. When did we start this? How much time left?
45 minutes.
Oh, 45 minutes. Okay. I thought it was 15. All right. So, what do we want to talk about next?
I remember something about something called flags in these kind of codes.
Flux?
Flags.
Right.
Like it's a
Flags.
flag something.
Yeah.
It's a bit different from the surface code. Can you explain that, or is it
No.
just something? I just wanted to understand.
No. Let's not do that.
Well, you can explain it to me later.
Yes. This is about fault tolerance. Okay, so okay, there are a couple of more things I want to talk about. Okay. We have bounds on code. So remember the classical LDPC achieved so nkd, remember number of bits, number of encoded bits, distance. You had k proportional to n and d also proportional to n, which is very good, right? It means that you're encoding at a constant rate, so you have a constant fraction of data per physical bit, and you can error correct a constant fraction of errors, which is great. Okay. In the quantum case, if you want stabilizer generators that are local in 2D, then we will have something like this. K d squared less or equal to something proportional to n. There's a small constant here, a constant, a numerical constant. Okay? So that's pretty bad. It means that we can't have both k and d scaling proportionally to n. In fact, it's much worse than that. Okay? So what do I mean by local in 2D? Imagine that you have a grid of qubit, and every stabilizer generator fits inside a ball of a constant radius. Okay? Doesn't matter what this constant is. So if you don't want long-range stabilizers, this is the best you can do. We'll talk about the surface code next, and the surface code actually saturate this bound. So surface code, we got k equals 1, d equals square root of n. Saturates this band. So in fact, we can prove more. We can prove that any code that is local in 2D is, well, okay, so I'm going to be telling you about the surface code. And let's say that as a homework, I ask you, come up with a new distinct code in 2D. One thing you could do is stack two surface code on top of each other and just like, displace one a little bit. So this is going to look like a new code in 2D. Instead of having coupling of range 1, it's going to have like range 2 couplings. And but I would probably detect that and call it a cheat. So I wouldn't give you your points, okay? So if you want to be more clever, you're going to take two copies, move them a little bit, and then maybe to trick me, you're going to put a bunch of control knots, just locally. So you're going to try to kind of blur what you did locally, okay? So you see what I mean? And by applying these local C0, you're not changing the amount of encoding data, and maybe you're like halving the minimum distance because you've applied a bunch of 2-qubit gate. So you could take a weight x error and turn it into a weight 2x. It turns out that this is the only thing you can ever do. So all codes in 2D are equal to a bunch of copies of the surface code, maybe up to some local gates. Okay? So that's the surface code is all there is in 2D. That's kind of very disappointing. So you got to go beyond 2D. Local, yes. So if your stabilizers are local in 2D, what you got is the surface code, 2 surface code, 3 surface codes, and so on, which are less and less local, but they're all constantly local. Okay. All right. So we will want to avoid 2D. It would be great to have something like this. Okay. The next thing I want to talk about is gates. So So we want to do gate in these codes. So universal gates. The standard universal gate set in these code is Clifford plus T. This is a universal gate set, meaning that you can achieve any unitary on n qubit by composing elements of this. The Clifford is formed of the Hadamard, S, which is the square root of Pauli Z, and the C naught. Okay? And T is equal to square root of S. No, 8.
So you could define the Hadamard as square root of x plus z.
Hadamard as square root of x plus z. X.
Plus z.
Yeah, Hadamard. I will define them. The way I like to define gate is by their action on Pauli matrices. Okay, so H has the following action. So if I take X, it goes to Z, and Z goes to X. This is the action of Hadamard gate. It just exchanges X and Z. Okay? Those I've defined. And the C naught, it acts on 2 qubit, so it takes Z identity to Z identity, IZ to ZZ, X identity to XX, and identity X to identity X. Okay, so have most of you seen these things before? Who has seen this before, this truth table? Okay, so this is just like, what I mean here is that if you take some operator P and then you conjugate it, okay, you get another operator, and this is what I'm defining here. The fact that these gates map map Pauli matrices to Pauli matrices is special. Not every gate transforms a Pauli matrix into another Pauli matrix, and this is the definition of the Clifford group. It's a set of transformation that map Paulis to Paulis. You can check explicitly that this does not map a Pauli matrix to a Pauli matrix. It maps it to something else. Okay? So, any questions about this? So we've talked about transversal gates in the classical setting. And recall je me suis trompé avec le pi over 4. Yeah, oh, yes. Sorry. Yeah, sorry. Over pi would be -1, square root. Yes, thank you. Recall that transversal gate map, or I should say, don't increase the weight of errors. It is the same. So you will have a bunch of qubits. This will be your logical qubit 1, and another block here. This will be your logical qubit 2. And a transversal gate would be one that does, and here I'm just drawing the topology of the gate, does something like this, or acts individually on every qubit. So it does not spread errors within a code. Okay? So if you had a correctable error to start with, it will remain correctable. So this is a systematic way of constructing fault-tolerant gates. Okay? No, so systematic way of constructing fault-tolerant gate. Right? Because if all your logical acted this way, you would never increase the weight of the error, and therefore a correctable error would always remain correctable. So if you you always, in your computation, you have logical gate, error correction, logical gate, error correction, logical gate, error correction, then you'll catch every error, and you'll be able to correct them. But if they're not transversal, maybe you do error correction, your logical gate spreads errors, and then you can't correct it. Okay? There's a theorem. No quantum code admits a universal set of transversal gate. This is a theorem due to Knill and Easter. So recall this is in contrast to the classical case where we had this one universal gate, the NAND gate, and we could do it transversally, so we were good. In quantum, this cannot occur. Okay? So typically what will happen is that for a lot of codes, including the Steen code and some version of the surface code, we'll get the Clifford gates for free. Not for free, sorry, transversally. So these will be naturally fault tolerant. And then we'll have to work hard for the T gate. Okay? In many codes, Clifford are naturally fault tolerant. And extra work is required for the T gate. Why am I saying this? Because this will be the case for Ldpc code. If time permits, I will show you how to do the Clifford gates in a fault-tolerant way in quantum Ldpc codes. But the T gate will require some extra work. Okay? Let me, yes?
It's only true for binary code or also for continuous?
Yeah. There's this thing about continuous variable codes. Well, yeah. Yeah, okay. So if you go to QDITS, higher dimension, what you can do is have transversal gates, universal transversal gate, but the code is approximately error correcting. Okay, it does not correct exactly, say, weight 1 errors. The amount of approximation is 1 over d, where d is the you know, the dit, Q dit. So if you had very, very large dits, you could, if you have very large Q dits, you could potentially have a universal transversal gate set. However, how small do you want this error, right? If you have a quantum algorithm that requires 10 to the 10 gates, it means you would have to have 10 to the 10 level systems, right? Because that's the remaining error. So I mean, in the past couple of years, people have punched holes in this theorem. The theorem is right, but they have found ways to relax the underlying assumption and to get around it. These continuous variable codes are one way to do it. And there's also, nothing says that the entire computation needs to be done in the same code. Okay? So there are ideas called code switching, where during the computation you change code, and then you can do some gates here, some gates there, and there are techniques for this. It's hard. I mean, there are techniques also to make sure that the switching itself is fault tolerant. It's not obvious. Okay? But yeah, there are a couple of ways around this. Okay, and in the notes I give other sort of no-go theorems that are more sophisticated than the one I just described. So just for sake of completeness, let me tell you how we deal with the T-gate. Okay, because like in this lecture, I will only show you how to realize Clifford gates. And you might wonder, you know, that's not universal. In fact, that's something I can simulate on my laptop. So I won't build $1 billion computer to do something I can simulate with my laptop. I want my T-gate. And let me show you how it's done.
That's what the alpha says to you?
Give me my T-gate. So we're just going to move the problem around, okay? So we want to do a T-gate. We don't know how. So we're gonna do something that is called state injection. So this thing requires a magic state that we call A that is equal to T applied to plus. Okay, so it is, well, plus is just 0 plus 1. So it is 0 plus e to the I pi over 4, 1, divided by square root of 2. Suppose we have access to a supply of such states. Okay, for some magical, well, they're called magic states, so let's not worry about where they came from for now. Okay, it's just magic. Okay, let's analyze this circuit here. So I'm going to stick my magic state here, and I'm going to have some arbitrary state. I'm going to do a control naught, and I'm going to measure this guy here in the Z basis. So let's first, so the initial state is alpha 0 plus beta 1. This is psi with 0 plus e to the I pi over 4, 1. I'm going to drop normalization. Okay. Okay, then we do a C naught. Remember, the C naught will flip the second bit if the first one is 1. So we'll get alpha 0, 0 plus e to the I pi over 4, 1, plus beta 1, 1 plus e to the I pi over 4, 0. This is what the C naught does. Let me just rearrange these terms by isolating 0 and 1 on the second qubit. So this is equal to 0 has alpha 0 plus e to the I pi over 4, 1, beta, thank you. And then let me isolate the 1. This will be, I want to isolate, yeah, okay, so it will be alpha e to the I pi over 4, 0 plus beta 1, 1. All right? So now we measure the last qubit. If we get 0, we're good. We've just applied a T-gate to our state. This is great. If we get the 1, we sort of, so after measuring, I could move this phase here up to a global phase. I could move it. It would just have the wrong sign. Okay? So this is proportional to T dagger psi. So if we get the 0, we're good. We have what we wanted. If we get 1, it seems like we've messed up our data. But this is okay, because if I multiply by s, remember t is the square root of s. So now I sort of have, so you should think of s as t squared. Okay, so you get one of them cancels the t dagger, and you're left with t psi. Why was I allowed to do this? Because s is a Clifford. Okay, so if you get 0, you've applied, you're good. If you get the 1 up to a Clifford, you're good. And this circuit required only the C0, which is Clifford as well. Yes?
Where do these additional qubits come from before?
The A.
Yes.
Yeah, it's magic for now. Yeah.
It's a magic state.
Yeah, it's a magic state. But what I want to show, what I've shown so far is that I can trade a T-gate. If I have Clifford, if I'm already able to do Clifford, I can trade a T-gate for an A state. These are kind of the same resource. Okay?
It's like you have to have another quantum computer on the side.
No, I'll explain this next. But I mean, for now, I can trade a T-gate for an A state.
For a logical state, right?
Yeah, a logical A state. Yeah. Okay? So far, so good? Yes.
You're also increasing the weight of errors by measuring, right? Or you just,
I am yes. Okay. So when I say that a code has fault-tolerant Clifford operation, what does Clifford operation actually encompass? It encompasses the gate I described, Hadamard, control not, S, but also preparation of zeros and 1, and measurement in the computational basis. I can do all these things fault-tolerantly in many code. I should have been clear about that. Yeah, I was not. So everything that is done here is fault-tolerant, except this A state. So what's the deal with this A state? Well, it turns out there exists protocol that we call magic state distillation. These will take as input a bunch of crappy A state, and it will output a higher quality A state. Okay? So to prepare A, we non-fault tolerantly prepare many encoded A. We can do this, right? It's not fault tolerant. So this requires non-Clifford gate, and we just do them like by brute force. Okay, so there will spread error. These guys will be error prone. And we prepare a bunch of them. And inside this code, we simulate another error correcting code that has a transversal T-gate, essentially. Okay, that's the idea. And this will correct our A state. Yes?
Can you shoot it for this state, that is the T-gate being fault-tolerant and other gates, and the exclude fault-tolerant the other gates?
Repeat, please.
Like you say that you're going to use another code, inside the magic state?
This is, no, this other code is all inside this error correcting code. So we're working with a base level code that has Clifford for free. In this logical space, we're going to do error correction, higher level of error correction. This higher level error correction that we're doing has a transversal T-gate. We're going to use this to error correct these noisy logical A state.
So you will require non-faulty, one of the non-faulty gates because of the theorem.
Yes, yes, but yes. This code that we're emulating inside the first error correction code uses only Clifford, like every quantum error correcting code. But it happens to have a transversal T-gate. So it can error correct these noisy A states.
Oh, you don't care about the other errors, which are not non-faulty.
There are no other errors because everything's happening inside a code. There are no other errors. That's right. So this thing would not have all the gates but we don't care about this. This is all happening in the virtual world. So at least I think one person got it. Anyone else? Yes. 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 Sorry?
Can you apply this method to other states?
We do not have general purpose distillation protocols for most state. No. I mean, like the fact that it's pi over 4 is sort of very important. And it comes out like, yeah, there's a lot of kind of magic happening when you do these things. It's hard, like, for general states to come up with distillation protocols. The kind of thing that helps, the trick here is that also this cannot be prepared by Clifford operation. It is an eigenstate of Clifford operation. It's an eigenstate of S. Okay? So that's kind of what's helping here. Yes?
Could you give us any idea, like, just some intuition for what the code that has a transversal T looks like?
It would be a little bit tricky. I can do it. No, we're out of time, are we? 15 minutes. I can finish with that. I don't mind. Yeah, I can finish with that, and then we'll talk about Surface Code Friday. Okay. Yeah, that might be very helpful, in fact. So let me just give you the tell you what we'll do in the next classes. So what we'll do, okay, I'll explain to you how to get a transversal gate set, a transversal T-gate. And then Friday, I will explain the surface code with this very kind of weird formalism. But then once we have this formalism, we can just plug everything we've learned about Ldpc in this formalism. Okay? So I was planning to do that Friday, but you'll just have to that's kind of the simple part. Okay. So transversal gate. I will, instead of doing exactly what you asked me, I will show to you that the Steen code has transversal Clifford. And when we understand why the S gate is transversal in the Steen code, you'll understand how to get a transversal T gate. Okay? The argument is very similar. All right. So let's write our parity check matrix. Okay. So this is the Steen code. And then you make a copy of this with X's, a copy of this with Z's. Right? Okay. So, okay. So, okay. We have to define logical operators. Okay? So these are logical operator. What do I mean by this? These commute with all the stabilizers, right? And then okay. Is it clear to everyone that these commute with all the stabilizers? Yes, it is, because they all have even weight, so they will anti-commute with all of those an even number of times. Okay. They also anti-commute with each other, which is what you want of logical X and Z operators, right? Because X and Z anti-commute, you want the logical incarnation of these operators to also anti-commute. So these are the operator you use if you want to manipulate your logical data. Okay? So let me show to you that the let's start with the Hadamard. If you want to do a logical Hadamard, what will you do? So a logical Hadamard should do two things. It should swap these two guys, because that's what a physical Hadamard would do. It would, on a single qubit, a Hadamard swaps X and Z. So you want your logical Hadamard to swap your logical X and your logical Z. But you also wanted, so if you start in a state psi and you apply this logical Hadamard, you want this to still be a +1 eigenstate. Right? So you still want to be in the code. Let me write this way. Is that how you... Okay, yeah, let me just multiply by h dagger. Okay, I've just multiplied by h dagger. Excuse me? Yes, thank you. These guys cancel. Okay, Hadamard dagger is really Hadamard, but this is not a problem. So this means that if this is true for all psi, this guy must be a stabilizer. Okay? So here's what you want. You want your logical Hadamard to swap those two, and you want to take those guys into the groups generated by those guys. They don't need to stay put. They can move around, but you want each one of them to remain in the same group. Okay? Is that clear to everyone? That's what you want out of a logical Hadamard. I claim this will do it. All right? Well, if you apply Hadamard to every qubit, you're going to just exchange the role of X and Z. So you're going to swap these. This is what you wanted. And you're going to swap this top part and this bottom part. So you still have the same generator group. You've just moved the generators around. Sorry. You still have the same stabilizer group. You've just permuted the generators. Still the same group. Okay? So this is a transversal Hadamard, and it does a logical Hadamard. Everyone good with that? Okay. So next thing we want, so I'm doing the easy ones now, but the easy ones now. We want a C0. All right. So this is a little bit more tricky because a C0 acts on two logical qubits, right? So we want C0 should take Z bar identity to Z bar, Z bar. Yeah, right. It should just have the same truth table as the unencoded C0. I wrote the truth table before, right? So that's the truth table I want. it's pretty obvious that if I apply, so now I have my two codes side by side. If I apply a transversal if I do this thing, and so on, it is pretty clear that whatever the effect was on the individual bit is going to be copied onto the logical bits, right? Because the logical bits are just a bunch of copies. Okay? So it's going to have the right action on the logical bits. Everyone good with that? It's going to have the right action. What about the stabilizer? Okay? So the stabilizer of these two things, I can write this way. It's Sx tensor I times Sz tensor I times I tensor Sx times I tensor Sz. So what I mean by each of those is the group of all three. So I'm writing this now as a group. Okay? It's the group generated by these guys times the group generated by those guys, and so on, right? So these are the stabilizers acting on my first code. These are the stabilizers acting on my second code. Under the C0, this will be mapped to Sx tensor. So any operator that's x, a bunch of x on the first and identity on the second, if I apply C0, according to this truth table, nothing will happen. Then here I will have Sz. Okay, so these guys change. Here I will have, and here I will have, no, sorry, this is bad, Sx. And identity tensor Sz. Right? This is how the stabilizer generators will be transformed. But they generate the same group, right? Because like if I'm unhappy with this Z, I can multiply by this guy and cancel this S. So whatever I was generating with those, I generate the same group with this. Right? I've just kind of multiplied stabilizers together, but I generate the same group. That good? So we got ourselves a transversal Hadamard, transversal C0. We're missing the S gate. This is where the magic happens. Okay? Everyone with me so far?
I think xi should go into xx.
X.
I mean, even that there, xi should go to xx.
Yes, I got those wrong. I got those wrong. X bar I goes to X bar. No, sorry, X bar, yep. I X bar goes to I X bar. Oh, so these are wrong. Sorry. Yeah, they're all wrong. They're all flipped. Sorry. Or I could have just changed my control around. Okay, so this is probably all wrong for the same reason, but I think you get the argument, right? I'm just kind of moving my generators around, but always generating the same group. Okay, so far, by the way, everything I've done generalized to any self-dual CSS code. I've only used the fact that the X and Z stabilizers are the same, so I can swap them around in anything, and it's good. So we've just learned something. Every self-dual CSS code has transversal Hadamard and transversal T. It's pretty good. Okay, what about S? S gate, remember, is the square root of Z. This one is going to be special. Okay, so to answer this question, to understand how the S works, and this is going to help us understand how the T works, it's going to be the same but just a bit more sophisticated. What is my logical zero? What's the log? I want to write it now as a ket. So by definition, I should have Sj 0 bar equal to 0. Sorry. Right? It should be in the code. And second, I should have Z bar 0 equal to 0. That's kind of the definition of 0. It's a plus 1 eigenstate of z. So in terms of the logical z, it's going to be a plus 1 eigenstate of the logical z. The logical 0 is going to be plus 1 eigenstate of the logical z operator. That entirely defines my 0 state, right? It's the state that's in the code that's a plus 1 eigenstate of my z operator. That's a z, logical 0. All right, so let's try to construct this guy. Let's start by our vacuum state, which is, all right, that's a guess. Okay, it's a guess. Is it the actual logical 0? Is it a plus 1 eigenstate of this? Yep. Check, we're good. Is it a plus 1 eigenstate of this? This? Pretty good, eh? But we have a problem with those. So what we're going to do is we're going to take this state and we are going to project it on the plus 1 eigenstate of each one of those. Okay? So we're going to take, what's the projector? I claim that P equals 1 plus S over 2 is a projector on the plus 1 eigenstate of S. Everyone sees this, right? Because S has plus and minus 1 eigenvalue, so the minus 1 goes to 0 and the plus 1 goes to 1. Okay? So this is the projector. So what I'm going to do this. I'm going to do a product over J equals 1, 2, 3. 1 plus Sj, the X type, and divided 1 over 8. I don't care about this. Or at least it's proportional. By projecting, I'm reducing the amplitude. Okay? Everyone understands this? So there's a bit of thinking going behind this, because we agree that if we can fix those three eigenstate, those three, we'll have ourselves a logical 0. Now, if we manage to project on their plus 1 eigenstate, we'll be good. But you might worry, won't we be messing up the good eigenstate by doing this, right? Was anyone worried about that? Well, no, because they commute. Okay, all these operators commute. So by doing this, you know, if you were a plus 1 eigenstate of z, you can pull that one right here. So you're not going to mess up the plus 1 eigenstate that were good. Okay? So this completes the proof that this is your logical 0. But now let's expand this. So we have a product. I want to expand this product. I claim that this is equal to the sum over all S in the X part of the stabilizer right? Because I would have, if I expand the product of these three things, 1 plus S1, 1 plus S2, 1 plus S3, I will get 1 plus S1 plus S2 plus S3 plus S1 S2 plus S1 S3 plus, right? I just get the sum over everything in the group. Is that good? So I can say this is equal to the sum of every x in the row space of my Hamming code. This is my logical 0. Are we all good? This is my logical 0. What's my logical 1? The logical 1, so this is my logical 0. My logical 1 is just the complement of this, right? Sorry. And I want to, let's say negation. What's the negation symbol? Something like this. I just like flip 1s and 0s. because this is what the logical X does. Okay, so we know now we got ourselves a logical 0 and a logical 1. All right, so let's test our S gate. Okay, let's just try the first thing. Let's try S bar equals S to the 7. Why not? Okay, so what will happen to 0? So sum over all x element of the row space of x will be mapped. So the S, remember, S is 1, 0, 0 e to the I pi over 4. So here it will go to sum over x. I'll just drop this. E to the I pi over S, yes, I'm doing S now. Thank you. T was over 4. So every time there's a 1 in x, I get a phase. Every time there's a 0, I don't get a phase. So my total phase is just the number of 1s in x. Okay, but here's the cool thing. Remember this matrix. The row space contains 0, the all zeros vector. This will pick up no phase. Everything else it generates has weight 4. You can see those guys have weight 4. You can add them together. You only generate things of weight 4. So I can replace this by a 0 or a 4, and it doesn't matter, right? Nothing happens. Everyone sees that? So it's just because, you know, the weight here is 0 mod 4. That's all I care about. Let's check what happens with the 1. It was the negation. Same thing, right? No, pi over 2. The weight of the negation of x. X. What are the possible weight of the negation of x? Well, the all 0 string, the negation has weight 7, right? It will be the all 1 string. The other one will all have weight 3. So they're all weight 3 mod 4, right? Because 7 is 3 mod 4. So this is equal to e to the minus I pi over 2. Or if you want, I can put 3 pi, or minus 1, 1 bar. So we were off. There you go. So what we did is an S dagger. Okay? So you understand now. Was that clear? Yes?
Why do I have mod 4?
Well, okay. Well, okay, because of course here, if I add multiples of 2 pi, doesn't matter. Okay, so if I only care about the weight mod 4.
Because it changes the...
Because like if I multiply by 4, I get 2 pi. So I don't care about 2 pi's. Okay? And these guys happen to all have weight 0 mod 4. So this guy doesn't pick up any phase. The complement all has weight has weight 3 mod 4. So it picks up 3 pi over 2, or minus pi over 2. Okay? So it implements the adjoint of this transformation. So now you see right away what you need to have a transversal T-gate. You need something that has weight 0 mod 8. Okay? If you have 0 mod 8, you're good. Okay? There is a code that has this. It's a Reed-Muller code. It's 15 bits. And all the stabilizers have weight 0 mod 8. That's it. That's the recipe. So we use this code to distill a T-state. Okay, so I've gone over time. Are there any pressing questions? Yes?
This code that you described, what is
non-fault tolerant gate?
T.
But I think he's asking
Oh, okay.
actually which gate in the
In the Riemann-Muller?
do transversally.
In the Riemann-Muller is not self-dual, so it does not have H. Yeah. Yeah. Good? Other questions? All right, let's go for lunch. Dinner.